Hello everyone, my name is Daniel Wynn and the material in this video is focused on thermal inspection in advanced packaging. This content is brought to you by work done in the Security Assurance Lab, also known as the SCAN Lab, at the University of Florida under the supervision of Aslam Khan, Changjie Shi, and Dr. Naveed Asadi. The material for this video will be going over thermal inspection of advanced packaging, where I will be outlining the following topics: a general overview of thermals in electronic packaging, material thermal properties, thermal interface materials, thermal performance, thermal measurements, thermal scanning techniques, especially thermal reflectance microscopy and Lockin thermography, and then I'll be finishing out the presentation with the glossary and references. First off, I will be discussing about a general overview of thermals in electronic packaging, specifically advanced electronic packaging. In advanced packaging, it is required to have effective thermal management. Advanced packaging is all about improving capability whilst making packaging smaller. However, smaller electronics tend to generate more heat in tight spaces. And without effective thermal management, this can lead to overheating, material stress, and device capability throttling, which can cause device malfunctions or failures. The figure on the right shows a heat map of integrated circuits and the thermal ranges they can experience from just different placements of the through-silicon vias. Optimal and adequate thermal management can ensure a user's safety, preventing possible burns, fires, and explosions. There are different ways to improve the thermal management in electronic packaging, and the materials used are one of the most important. To be more specific, thermal interface materials, aka TIMs, are intermediary materials, typically made from silicon, adhesives, or soft metals that sits between two components in electronic packaging to improve heat transfer, as shown in the figure in the bottom right. TIMs are designed to improve heat transfer and fill microscopic gaps and irregularities on the surface to reduce air, since air is an insulator that can impede overall heat flow. TIMs have a high thermal conductivity, which heavily reduce thermal resistance at the interface between components. These desired thermal properties can help give optimal thermal management in electronic packaging. Some of the most important types of material thermal properties are thermal conductivity, thermal resistance, specific heat capacity, thermal expansion coefficient, and thermal diffusivity. Thermal conductivity is a material's ability to conduct heat. As most recently stated, this is incredibly important for the thermal interface materials to help improve heat transfer in an electronic package. Thermal resistance is a material's ability to resist heat flow. This is important in insulators used in electronic packaging to contain heat in certain areas or protect the components from external heat. Specific heat capacity is the energy needed to raise the unit temperature by 1 degree Celsius. These materials can absorb more heat, protecting components during thermal stress. Thermal expansion coefficient is how much a material expands when heated. Because of this, different materials within electronic packaging are chosen with similar coefficients to prevent thermal expansion mismatches. And finally, thermal diffusivity is how fast a material dissipates heat, which allows heat to spread away from the hot spots quicker. Bad thermal performance in advanced packaging can cause a lot of issues, failures, and malfunctions in the devices. Hotspots, as just recently mentioned, are one of the most important factors of thermal performance. They are areas in the electronic package that show significantly higher temperatures compared to their surroundings, as shown in the figure on the right. These hotspots can cause localized high temperature degradation. Another issue that can arise from poor thermal performance is thermal cycling stress from repeated thermal expansion or contraction. Moreover, if different materials within the electronic package have different expansion rates, their thermal expansion mismatch can cause unnecessary stresses and delamination to occur. Furthermore, inadequate thermals can cause electromigration with increased metallic ion movement to create voids, and there can be an increased rates of oxidation and corrosion, which can eventually cause failures in the devices. Continuing with poor thermal performance, especially due to high temperatures, is decreased semiconductor performance. Having higher temperatures can slow the intended operating speed of the device. And building off of that is that the material making up the device itself can start degrading, altering important properties such as lowering electrical conductivity. The degradation of the device can lead to a reduced lifespan, increasing the risks for failure and making room for possibly thermal runaway, where uncontrollable temperature increases occurs and thus degrading the device even further. Visually, operators can detect and measure these thermal changes and side effects using different thermophysio inspection imaging devices. Some advantages to using external thermal scanner devices are that most make no direct contact with the device, making them non-destructive. They also have instantaneous imaging, wide temperature range detection capability, and high resolution imaging. Some disadvantages directly tied to the devices are possible misreadings due to bad surface emissivity, environmental interference such as external humidity, dust, and ambient temperature, and possibly limited depth perception, as not all scanners provide information past the surface. Some disadvantages that external thermal scanners have, but are not directly tied to their technology capabilities, is that high quality scanners can be very expensive. Moreover, operators of the scanners must be knowledgeable about how the scanners work and the data they collect in order to mitigate external disadvantages and to have correct interpretation of data. There are a variety of thermal scanner techniques, and they can be broken down into their different technologies for thermal analysis, as shown in the chart. Thermography-based scanners are ones that utilize cameras or sensors and can detect the heat emitted from devices. Microscopy scanners are scanners that utilize microscopy and their lenses to detect temperature-induced changes. Wave-based scanners are ones that utilize thermal waves to propagate throughout the object, and then the response returned is what is measured. As for the actual techniques themselves, I'll begin with infrared thermography. They utilize IR cameras to capture and measure infrared radiation from an object's surface, which provides a temperature map or a thermal image. Lockin thermography is a method where thermal excitation is modulated at a specific frequency, and then the thermal response is measured. Raman thermography combines Raman spectroscopy with thermal measurements to provide temperature maps based on the Raman shift, which is sensitive to temperature changes. Liquid crystal thermography uses thermomic liquid crystals that change the color based on temperature, allowing for temperature mapping on a surface. Optical beam-induced resistance change, also known as OBERT, detects local changes in electrical resistance caused by a focused laser beam, which can be related to the temperature changes in the material. And near-infrared emission, also known as EMI, measures the near-infrared emission from semiconductors, which is often used to detect defects or overheating components. For microscopy-based techniques, we'll move on with thermal reflectance microscopy. Thermal reflectance microscopy measures the changes in reflectance is due to temperature variations, which allow for high-resolution thermal imaging at the microscopic level. Moreover, scanning thermal microscopy is a technique that uses a probe that can scan the surface to provide localized temperature measurements with high spatial resolution. And moving on to wave-based techniques are thermal wave imaging, which utilizes thermal waves generated by periodic heating and employs phase-sensitive detection to measure thermal properties in subsurface structures. Photothermal radiometry is a non-contact technique that measures the thermal radiation emitted from a surface after it's been heated by a source, making it useful for analyzing surface and subsurface features. The near-infrared emission is listed again in wave-based techniques because it has very versatile applications, as it can detect thermal emissions across various scenarios, including wave-based techniques. Moving on is categorizing these thermal scanner techniques into the areas of focus and what they focus on. For the macroscopic scale techniques, you have infrared thermography, liquid crystal thermography, photothermal radiometry, and near infrared emission. For microscopic scale techniques, you have thermal reflectance microscopy, scanning thermal microscopy, Lockin thermography, and once again, EMI. For materials characterizations focused techniques are thermal wave imaging, Raman thermography, Lockin thermography, and optical beam induced resistance change, OBERG. One of the main techniques I will be focusing on in this presentation is the thermal reflectance microscopy, as there is one located in the scan lab. The TRM is a technique that operates on the principle that optical reflectivity of most materials change with temperature due to changes in the material's refractive index. With this, the sample gets heated and the reflectivity changes, and these changes are captured and translated into temperature measurements. And the mechanisms that comes along with this technique is that, as I just said, with reflectance change, the measurements are in high resolution. The measurements are recorded in dynamic real time, and once again, they are non-contact. Applications for thermal reflectance microscopy includes hotspot identification, material thermal property testing, thermal interface materials evaluation, and design optimization. As shown in the figure in the bottom right, that is a picture of a TRM from Microsange. Shown in the image in the top right is an image of transient thermal imaging from TRM. And the sequence of images demonstrates the material's response to heat over time, providing insights into its thermal conductivity, diffusivity, and efficiency of heat spreading. This analysis is essential for understanding thermal behavior in electronic packaging, and more specifically HBM and 3D integrated circuit types, where managing heat is crucial for reliability and performance. One of the main techniques I will be focusing on in this presentation is the thermal reflectance microscopy, as the scan lab is focusing on this technology. The TRM is a technique that operates on the principle that optical reflectivity of most materials change with temperature due to changes in the material's refractive index. With this, the sample gets heated and the reflectivity changes, and these changes are captured and translated into temperature measurements. And the mechanisms that comes along with this technique is that, as I just said, with reflectance change, the measurements are in high resolution. The measurements are recorded in dynamic real time, and once again, they are non-contact. Applications for thermal reflectance microscopy includes hotspot identification, material thermal property testing, thermal interface materials evaluation, and design optimization. As shown in the figure in the bottom right, that is a picture of a TRM from Microsange. Shown in the image in the top right is an image of transient thermal imaging from TRM. And the sequence of images demonstrates the material's response to heat over time, providing insights into its thermal conductivity, diffusivity, and efficiency of heat spreading. This analysis is essential for understanding thermal behavior in electronic packaging, and more specifically HBM and 3D integrated circuit types, where managing heat is crucial for reliability and performance. Another thermal scanner technique that the scan lab is focusing on is Lockin thermography. Lockin thermography is based on the measurement of the temperature changes caused by periodic thermal waves that are generated by an alternating heat source. This thermography-based technique detects subsurface defects or inhomogeneities in materials. And the mechanisms that follow under Lockin thermography is that they have a periodic stimulus, phase-sensitive detection, defect mapping, and has heavy depth and can measure multiple depths within a device. Applications for Lockin thermography include defect detection, which is useful in quality control, thermal pathway evaluation, and material thermal property evaluation. The figure on the left showcases a sonde scope, which is a Lockin Thermography imaging camera system created by Microsange. The image on the right showcases the capabilities of Lockin Thermography and showcases the phase distribution for single defect and multiple defects separated by a large distance. These images and graphs are typically used to identify and characterize defects within these materials. The phase angle changes can be indicative of various material inconsistencies, such as cracks, voids, or inclusions, which can be critical for identifying the integrity and performance of electronic packaging, such as HBM. There are also the other techniques that were previously discussed but are not currently found in the scan lab. However, these techniques also have very high capabilities. The chart showcases these external thermal scanners mechanisms and their viable package types. For infrared thermography, their main mechanism is to identify hotspots. Liquid crystal thermographies is to surface or map surface temperatures. Near infrared emissions mechanism is to detect overheat and hotspots. Ober's mechanism is to identify thermal effects caused by localized failure. Photothermal radiometry's mechanisms is non-destructive thermal characterization. Raman thermographies is to identify thermal stresses and temperature. Scanning thermal microscopies is to identify thermal conductivity in a microscale. And then finishing off with thermal wave imaging's mechanism is to identify subsurface defects. Here's the glossary. Here are the references.